Swayam Prabha. Digital India. Educated India.
Hello and welcome to lecture 6 of module 7, where we were discussing numerical methods to solve ordinary differential equations initial value problems. What we started off with was Euler's equation, and in yesterday's lecture we considered one more example with Euler's equation and saw that Euler's equation under certain conditions becomes unstable. That means we go to minus infinity or plus infinity, or we have highly oscillatory behavior. So what I am going to do in today's lecture is going to talk about the stability issues with respect to the Euler's method, the implicit methods and the explicit method. Before actually going to that, what I will do is just spend a few minutes recapping what we have done so far. I think every lecture of this module we are just starting with recapping all of these methods, simply to put all these methods, because we are covering a fair number of methods in this particular module compared to any of the previous modules. So I want to put all these various methods that we are considering into perspective. For example, when it comes to some of my own work, my own research work, I tend to use not just one method, but I tend to try a few of these methods before figuring out that this method is going to work the best for me. There are cases where I have ended up using the second order RK method. There are cases where I have ended up using the fourth order RK method, and so on. As far as possible, we start with RK4 method, and wherever we find certain problems using RK4 methods, we will go to some of the less accurate methods, but some of them which are actually more stable, for example through implicit methods. So I will talk about the implicit methods and the explicit methods, compare their stability. We will just cover it with respect to Euler's method and then make general conclusions about how this is going to work. Okay, so that is going to be our strategy for today's lecture. So let us consider Euler's method. Okay, and Euler's method, explicit method, was yi plus 1 equal to yi plus h multiplied by f of yi comma ti. Okay, so this was Euler's explicit method. And Euler's implicit method yi plus 1 equal to yi plus h times f of yi plus 1 comma ti plus 1. Then we went on to the Runge-Kutta family of methods, and in that case I will talk about Yoon's method, RK2 version. Okay, so in Yoon's method, the RK2 version of Yoon's method, what we do is we write our K1 equal to f of yi comma ti, K2 is f of yi plus h times K1 comma ti plus 1. Okay, so at this stage what we can do is we could perhaps, not we could perhaps, we could write yi plus 1 bar 0 equal to f of y plus 1 bar 0, we could write this equal to yi plus k1. Okay, and then this particular function we will be able to write this as f of y bar 0 I plus 1, and our y I plus 1, okay, is yi plus h times s, and s is h by 2 multiplied by k1 plus k2. So yi plus h by 2 multiplied by k1 plus k2, k1 is nothing but f of yi comma ti, and k2 is nothing but f of yi plus 1 bar 0 comma ti plus 1. Okay. So this is the RK2 version of Yuen's method. The predictor corrector version of Yuen's method is this becomes a predictor equation, and recursive use of this equation becomes a corrector equation. Okay. So we have y I plus 1 bar 0 equal to yi plus h times, I missed the h over here, so I will just correct this thing, plus h times f of yi comma ti. Okay. And this is the predictor, and the corrector equation is y I plus 1 bar m plus 1 equal to yi plus h times f of yi plus 1 bar m comma ti. Okay. So that's the corrector equation, sorry, this is going to be h by 2 this plus f of yi comma ti. Okay. So this is what we are going to use as the corrector equation for the predictor corrector Yuen's method. Okay. And if we keep using this particular equation until convergence, we will get the Crank-Nicolson method. Okay. So what we mean by the Crank-Nicolson method is when this particular quantity becomes equal to this particular quantity, we call that particular iteration has converged, and we denote this as yi plus 1. So we replace yi plus 1 and yi plus 1 instead of y bar m and y bar m plus 1, and we will get this equation, and this is the equation that needs to be, it is a nonlinear equation that needs to be solved in this Crank-Nicolson method, which is a semi implicit method. Okay. So that is the RK2 version of Yuen's method, predictor corrector version, and the semi implicit method, which is essentially the Crank-Nicolson method for solving this particular problem. What we realize over here when we do this predictor corrector method is this is a trapezoidal rule. This being a trapezoidal rule has an order of h cube accuracy, but this is just an explicit Euler's method. Being an explicit Euler's method, this has an order of h square accuracy. Okay. So the question that we are trying to ask now is, can we actually do better in the predictor corrector Yuen's method than using an h square accuracy for the predictor? And the answer to that of course is yes, and we will have a more accurate version of the Yuen's method. So modification to Yuen's method okay, and this particular modification will be implemented in order to improve the accuracy of the predictor equation. Okay. In this case we will recall our result that the central difference formula during numerical differentiation were more accurate than the forward difference formula. Using basically parallel arguments to those arguments, we will convert this particular formula from yi0 equal to yi comma h of h multiplied by f of yi comma ti, will convert it into a slightly better formula. And what that better formula is the numerical difference dy by dt, we can write that equal to yi plus 1 minus yi minus 1 divided by 2h. Okay. Now dy by dt was equal to f of yi comma ti. Okay. As a result, our method with an improved accuracy is going to be yi plus 1 bar 0 is going to be equal to yi minus 1 plus 2h multiplied by f of yi comma ti. Okay. So that is the predictor equation, and the corrector equation remains the same, yi plus 1 bar m plus 1 equal to yi plus h by 2 multiplied by f of I plus f of I plus 1 bar m. Okay, I am just using shorthand notations over here because I do not want to write this entire expression all over again. So we have the equation dy by dt equal to f subject to y at 0 equal to some y0, right. So when I equal to 0, we are going to get y1 bar is going to be equal to y minus 1 plus 2h times f of y1 comma t1. But now the problem over here is y minus 1 is not known. Okay, we have started with, sorry, not y1 comma t1, y0 comma t0. We have started with an initial condition for y0. Okay, y1 represents the value at one time prior to this y0. Okay, and we do not know this particular value, this particular value is not given to us, this particular value is unknown. As a result, this predictor equation cannot be used at I equal to 0. Okay. So the predictor equation cannot be used at I equal to 0. As a result, this improved Yoon's method is not self starting method. Okay. In other words, what happens is we need a method, a different method to be implemented at I equal to 0. After that, from I equal to 1, 2, 3 and so on, we can actually start implementing the non self starting method. Okay. So how to get out of this problem? Well, to get out of this problem is straightforward. At I equal to 0, that means the first time that you are going to take the first step in this integration problem, okay, we do not implement the modified Yoon's method, but instead we implement the original Yoon's method. Okay. So at I equal to 0, the idea is implement the original Yoon's method, at I equal to 1, 2, 3 and so on, implement the modified Yoon's method. Okay. So the ad hoc solution, we can say, okay. So the way to handle this particular problem is at I equal to 0 we will use the original Yoon's method, which means the predictor will be of the form yi plus 1 bar equal to yi plus h times k1. So in other words, y1 bar 0 equal to y1 plus h times k1. That is what we use for the predictor. We will use this particular equation for the corrector. Keep in mind that the corrector equation has not changed from Yoon's method to the improved Yoon's method. Now when after we solve this particular problem at I equal to 0, we move on to I equal to 1, and I equal to 1 we can actually use this predictor, because y bar 2 equal to y bar 0, which is y0, which is a known quantity, plus 2h times f of y1 comma t1. y1 is known, t1 is known. As a result, we can now use this method. So a non self starting method, and Yoon's method is just one example of non self starting method. In the next lecture we are going to consider a few more examples. Specifically we will consider the Adam Bashford and Adam Moulton's family of methods, which are actually non self starting multi step methods, and over there as well we are going to use ideas similar to this. Is for I equal to 0 or I equal to 0 and 1, so on and so forth. We will use a less accurate method to get our method of choice started, and once the method of choice gets started we will go on and keep using our method of choice in order to improve the accuracy. Okay, so now what we have done is we have talked about the Yoon's method, RK2 method, we have introduced ourselves to the predictor corrector methods. Now we will go back and analyze what happened in yesterday's in the previous lecture of this particular module. What happened when we saw that the method using the Euler's explicit method did not converge, but instead we saw oscillatory behavior. So what we saw in previous lecture, we changed our PFR equation to a first order equation of the form dc by dv equal to minus 1 by 2 c to the power 1. Instead of 1.25 we changed it to c to the power 1. Okay, when we chose, and again starting with c at 0 equal to c0 equal to 1 unit, moles per liter, moles per meter cube, whatever that the appropriate unit might be, we started at that. Okay, we solved this particular problem at h equal to 1 and we got a stable solution. The solution was not very accurate using the Euler's method, but at least the solution was stable. We got concentration C at 5 as some finite value. Okay. Next what we did was we increased the h to h equal to 2. Okay. When we increased the h to h equal to 2, C0 was equal to 1, C1 we immediately saw became equal to 0, and after that it remained at 0. Okay. C2, C4 and so on were all equal to 0 for h equal to 2. So what we saw happening with h equal to 1 was something of this sort. Okay, what we saw happening at h equal to 2 was in one step itself the solution came to 0 and then it stabilized at 0. Okay. Next we considered a higher h equal to 2.1. At h equal to 2.1 what happened is C 2.1 was negative, C 4.2 was positive, and so on and so forth. So what we saw is we saw some amount of oscillations taking place in this particular system. Specifically when we plot concentration versus volume, what we observed was that the concentration drops and then finally reaches 0. Okay. So this is what we saw, and these oscillations for h equal to 2.1 were relatively small, they got damped and very quickly the final solution stabilized. Then we increase the h further and we increase the h to h equal to 4. Okay. At h equal to 4 we saw C4 equal to -1, C8 that we observed was equal to 1, C12 was -1, C16 was 1, so on and so forth. So what we had observed in that particular case was behavior of this type. Okay. So each alternate values was negative or positive, so on and so forth. Okay, that is the behavior that we saw for at h equal to 4, and finally when we increase from h equal to 4 to h equal to 5, I think we increase it to h equal to 5, okay, but any value greater than 4 will suffice. What happened was that C5, C10, C20 and so on started increasing, and finally the concentration just blew up. So if we were to plot this particular guy for h equal to 5, we will actually see a plot of this type. Okay, so what we see is that this guy keeps expanding and we will either reach plus infinity or minus infinity alternatively, as volume V tends to infinity. Okay, so this is what we saw with Euler's explicit method. Okay, so what happens over here in this range is that the solution converges monotonically. Keep in mind that this is a plug flow reactor. This is in physically in a plug flow reactor, the concentration cannot go in a fluctuating manner. It has to actually smoothly go to the final steady state. That is what we will physically observe in a plug flow reactor, in which a first order in which actually any reaction, any single reaction is taking place. Okay. The next case was when h was between 2 and 4. Between 2 and 4, what we saw was there were oscillations. Okay, and when h was increased beyond 4, we saw that the system was unstable. Okay, we will now go ahead and analyze this behavior for the Euler's explicit method, try to find out why we get this particular type of a behavior, and then we will extend the same analysis to the Euler's implicit method. Okay. So I will go back over here where I had initially written down the expression for Euler's implicit and Euler's explicit methods. We will now look at the Euler's implicit method. The equation that we started off with was of the form dy by dt equal to minus lambda y, okay, where lambda in this particular example was half. Okay. So now if we want to solve this particular equation analytically, we divide throughout by y and we take dt on the other side and we integrate, and we will get ln of y equal to minus lambda t plus constant c. At t equal to 0 we have y equal to y0, so concentration the constant c is going to be equal to ln of y0. Okay, and we just rearrange this and we will get y at any time t equal to y0 e to the power minus lambda t. Okay. Now exponential function is always going to be stable, limit as t tends to infinity, e to the power minus lambda t is going to tend to 0 for positive values of lambda. So the analytical solution is stable for lambda greater than 0. Okay. Plus the behavior of the exponential function e to the power minus lambda t with t is going to look somewhat like this. Okay, which basically means, and finally it should settle down at 0, it will not go below 0. This is the function y against t starting at value y0. Okay. So what we will see, so the two physical features of the analytical solution of this particular equation is, one, that the equation settles down to to y equal to 0, and its second thing is it settles down monotonically provided lambda is greater than 0. If lambda is less than 0, of course we are going to get an unstable solution. Now what we want from our numerical method is, the first thing is that the numerical method of our choice should converge to a value. What that means by it should converge to a value is that limit as I tends to infinity or limit as t tends to infinity, y should converge to a finite value. This is of course true only if we have the original analytical equation being stable. We are just considering those cases for now. Okay, so we want the value of yi to be equal to a finite value as I tends to infinity. Okay, so let us look at the explicit method first. Okay, so we will have yi plus 1 equal to yi plus h times f of yi comma ti. Okay, and the function f in this particular case is minus lambda y. Okay, so f of yi comma ti when we substitute over here is going to be minus lambda multiplied by yi. Okay, so we can write this as 1 minus lambda h multiplied by yi. Okay, so yi plus 1 is 1 minus lambda h multiplied by yi. Okay, that is what we get. So now this we can write it as 1 minus lambda h multiplied by yi multiplied by yi minus 1. So we will have this as 1 minus lambda h squared yi minus 1, which we can write it as 1 minus lambda h cubed yi minus 2 and so on, equal to 1 minus lambda h to the power I plus 1 multiplied by y0. Okay, now this is our value of yi. Now let us consider the three cases: the case where yi decreased monotonically, the case where yi had oscillations, and the third case where yi did not have any oscillations, but yi had oscillations but it was unstable. Okay, so the case of monotonic decrease is when we get yi behavior something like this, and with yi ending at y equal to 0 as I increases. Okay, for this to happen, okay, what we need is that 1 minus lambda h should actually lie between minus 1 and plus 1. Okay, that is required for stability, and this particular guy should be positive, that is required for monotonicity. Okay, so for this particular thing is that let's call the 1 minus lambda h as alpha for yi plus 1, or rather yi equal to alpha to the power I multiplied by y0. For this particular equation to be monotonic, we need alpha to be less than 1 and greater than 0. This is what the alpha should satisfy in order for this particular equation to stabilize monotonically. Okay, for us to observe some oscillations but not a whole lot of oscillations, okay, if let us say if alpha was equal to minus half, what we will get is y1 equal to minus half multiplied by y0. So y0 starts at 1, this becomes minus 0.5. Okay, next y2 is minus half multiplied by y1, and y1 is minus 0.5, so y2 becomes plus 0.25, y3 becomes minus 0.125, y4 becomes minus 0.0625 plus 0.0625, so on and so forth. So for this behavior we need alpha to be between minus 1 less than alpha less than 0, or actually I should be writing as equal to. When alpha is equal to 0, at that time we immediately will hit this particular value and then flatten out at y equal to 0, okay. And for the case where we get oscillation, for the case where we get instability, okay, we need alpha to be greater than the absolute value of alpha to be greater than 1, okay. That means alpha should be less than -1 or alpha should be greater than -1, okay. So these are the various 3 conditions, and let us evaluate the first 2 conditions now. Let's evaluate the first condition where 0 should be less than equal to alpha, should be less than 1, and we will substitute alpha equal to 1 minus lambda h. So we will have 0 less than equal to 1 minus lambda h less than 1, okay, or we can take 1 on this side and we will get this as -1 and this will become 0, okay. So we will have -1 less than equal to minus lambda h less than 0, okay, or 0 less than lambda h less than equal to 1, okay. So as long as h, now h is a positive quantity, so this becomes a redundant thing, okay. H we always know is going to be positive, so as long as the value of h is less than equal to 1 by lambda, we will get monotonic behavior, okay. So that's the first result, that the overall numerical solution of the Euler's explicit method is going to be monotonic and monotonically decreasing for a linear system as long as h is less than or equal to 1 by lambda. Okay. Now let us then consider the next question. When do we get oscillations? We get oscillations we will get oscillatory but stable behavior if alpha is less than 0 and less than -1, okay. That means -1 less than 1 minus lambda h less than 0, or -2 less than negative lambda h less than -1, okay, or 1 less than lambda h less than 2, or h should lie between 1 by lambda and 2 by lambda, okay. So if h is between 1 over lambda and 2 over lambda, we will get the system to be stable but oscillatory, okay. If h is negative, we will get the system to be unstable. If h is greater than 2 by lambda, we will get the system to be unstable again, okay. If h is greater than 2 by lambda, we will not only get the system to be unstable, in addition to being the system being unstable, we will also see oscillations. So system is both oscillatory and unstable, okay. So to summarize these results, okay. So summary for of stability results for Euler's explicit method is that if h lies between 0 and 1 by lambda, we will get monotonic and stable behavior. If h lies between 1 by lambda and 2 by lambda, we will get a stable though oscillatory behavior. If h is greater than 2 by lambda, we will get an unstable behavior, okay. So, I will start with 0 over here, okay. I will put a point a location 1 by lambda, put another location 2 by lambda, and then these are the values greater than that. If H lies in the red region, we have stable and monotonic behavior. If H lies in this yellow region, we have stable but oscillatory behavior. Okay, and if H lies beyond this, we have unstable behavior. Okay. So, let us go to the result of the previous lecture. In this particular case, lambda was equal to half. So, 1 by lambda is 2 and 2 by lambda is 4. Okay. Between 0 and 2 we get stable and monotonic behavior. Between 2 and 4 we get stable but oscillatory behavior. At 4 we get exactly oscillatory behavior, the oscillations do not increase, they do not dampen, they keep going like this, because when H equal to 4 we get our alpha value, that is 1 minus lambda H is going to be exactly equal to minus 1. Okay. As a result, y I is going to be minus 1 to the power I multiplied by y0. So, it is going to be y0 negative y0 y0 negative y0, it will keep switching between those values. That is exactly what we had observed through our numerical simulations in the previous lecture. And when H went above the value of 4, for example, when we took H equal to 5, what we observed was that the Euler's explicit method was unstable. Okay. So, that summarizes the stability results for Euler's explicit method. Similar stability results are applicable for most other explicit methods, for all other explicit methods also. Explicit methods have a limit on the step size h that you can use before the system becomes unstable. Okay. If you take a very large step size using the explicit method, we will have the system becoming unstable. In case of RK2 method, the stability envelope for explicit RK2 methods are similar to that we see for the Euler's method. When we go to RK3 method, the stability envelope is much larger compared to the Euler's explicit method. In RK4 method, the stability envelope is still larger. Okay. However, in all these cases there is a maximum value of H which depends on the value of lambda. If you go to a value of H which goes beyond that particular value, we will get this behavior of the numerical solution to be unstable. Unstable behavior of numerical solution has to be avoided at all costs for a system that we know to be stable. Okay. Now, this is where the implicit methods become useful. So, let us go back to our derivation that we had done for the Euler's explicit method. So, this is the derivation for the Euler's explicit method. I will repeat the derivation for Euler's implicit method. For Euler's implicit method, okay, for Euler's implicit method we had yi plus 1 equal to yi plus h times f of yi plus 1. Okay, and f of yi plus 1 is nothing but negative lambda multiplied by yi plus 1. Okay. So, we will go over here and write that down. Okay, and we will take this term onto the right hand side and we will get 1 plus lambda h multiplied by yi plus 1 equal to yi, which is going to give us yi plus 1 equal to 1 divided by 1 plus lambda h multiplied by yi. Okay. So this is the value of alpha. Okay. Now we know that for positive values of lambda the analytical solution is stable. So we are only going to consider positive values of lambda. The step size is always positive. Okay. So no matter what value of h we choose, any non-zero value of h that we choose over here, alpha value is definitely going to be 1 divided by 1 plus some positive number, which means that alpha is always going to lie between 0 and 1. In this particular case, for lambda greater than 0, alpha is guaranteed to lie between 0 and 1. Okay. No matter what value of h you choose, we know for sure that alpha will lie between 0 and 1, because alpha will lie between 0 and 1. This method, an implicit Euler's method, is what we call as globally stable. Okay. So no matter what value of h you choose, no matter how large a value of h we choose, we will always get the implicit Euler's method to be stable. Stability does not say anything about accuracy. So this stability property is the reason why the implicit methods are actually used. Now what I have done so far is I have talked about the various Euler's method, Runge-Kutta method and so on. We have discussed about accuracy of those methods, we have discussed about stability of these methods, we have discussed then predictor corrector methods, what we mean by predictor corrector methods. We have also looked at non-self starting methods. Okay. So this is what we have done so far. All of this discussion involved single variable problems. We had dy by dt equal to function f, okay, and that particular function was a single valued function. Now what we are going to do is to look at the extension to the multivariable case. Okay. So consider that we have the equations of the form dx by dt equal to f1x, dy by dt equal to f2x, and so on and so forth. Okay, let us just consider three variables x, y and y, z as the three dependent variable, and t. Okay. And we require the initial conditions, and initial conditions means x, y and z have to be defined at the same value of t0. So let us say x at t0 equal to x0, y at t0 y0, and z at t0 equal to some z0. Okay. Let us now consider Euler's explicit method. Okay. And in Euler's explicit method, what we are going to do is x at I plus 1. Okay. So x I plus 1 minus xi. So dx by dt we can write it as x I plus 1 minus xi divided by h, that is going to be equal to f1 of x xi, yi, zi, ti. Okay. And then we multiplied by h throughout, and then we take xi on to the other side, and the equation is simply going to be xi plus 1 equal to xi plus h times f1 of xi, yi, zi, ti. Okay. Likewise, we can write for yi plus 1 as well, yi plus 1 equal to yi plus h times f2 of xi, yi, zi, ti, and zi plus 1 equal to zi plus h times f3 of xi, yi, zi, ti. Okay. So, this is the overall expression that we get. Now, let us write this in a vector notation. In vector notation, this we will choose our vector capital X as nothing but x, y and z, and our vector capital F as nothing but f1, f2 and f3. Okay. So, this we can be written as x I plus 1, y I plus 1, z I plus 1 is going to be equal to x I, y I, z I plus h times f1, f2, f3 computed at time I. Okay. So, this guy is nothing but our capital X I plus 1, this guy is nothing but our capital X I, and this guy is nothing but our capital F computed at xi comma ti. Okay. And this is our multivariable Euler's equation. So, in the vector notation, the equation that we need to solve is going to be d capital X by dt equal to some capital F of capital X comma t, okay, where capital X is in general a vector, capital F is also a vector. Okay. The Euler's explicit expression is going to be x I plus 1 equal to x I plus h times f of x I comma t I. Okay. This is going to be Euler's explicit. Euler's implicit will be x I plus 1 equal to x I plus h multiplied by f of x I plus 1 comma t I plus 1. This becomes the Euler's implicit method. The same idea we will extend it to the Runge-Kutta second order method. Let us talk about, since we have been doing Yoon's method in this particular lecture, we will talk about Yoon's method. Okay. In Yoon's method, our K1, capital K1 of x comma, or we just write this as capital K1, is going to be equal to f1 of xi comma ti, f2 of xi comma ti, and so on. Okay. So, capital K1 we can write as equal to capital F of xi ti. Okay. then we can write our K2, or before writing K2 we will write our y bar or x bar, sorry, x bar 0 I plus 1, we will write that as nothing but x bar, sorry, x I plus h multiplied by K1, okay. That becomes our next expression, okay. Our K2 is going to be nothing but function f computed at x bar I plus 1 0 comma t I plus 1, okay. And our final expression for Yoon's method is going to be x I plus 1 is equal to x I plus h by 2 multiplied by f of x I comma t I plus f of x, or I will just write this as equal to K2, K1 and K2 is going to be just h by 2 multiplied by K1 plus K2. Okay. So, this is our equation for the Yoon's method, where K1 is computed as f of xi comma ti, K2 is computed as f of xi plus 1 bar ti plus 1, and xi plus 1 is xi plus h by 2 multiplied by sum of K1 plus K2, where each of these capital letters are not scalars, but they are vectors of the same dimension. Okay. So, that is where we finish our this lecture of this module, of the 7th module. In the next lecture, what we are going to do is we will revisit the RK method, and we will talk about what is known as the adaptive step sizing, and finally we will just introduce ourselves to the Adam-Moulton and Adam-Bashforth family of methods. That is what we will do in the next lecture. And in the final lecture, I will finish off with the Adam-Moulton and Adam-Bashforth family of methods and do an overall recap of this particular module. Okay. So, I will see you in the next lecture. Thanks.